Welcome back to the deep dive. If you work anywhere near the world of AI, you know there's this single biggest headache in large language model inference. It's not the complexity.
No, not at all. It's that agonizing trade-off.
Exactly, the trade-off between speed and quality. For years, you've basically been forced to choose. Do you want that really high fidelity, perfect output from a traditional model?
Or do you want the blistering speed you can get from, say, a parallel architecture? You couldn't have both.
It really is the defining conflict in efficiency right now.
It is. The traditional models, the autoregressive ones or AR models, they give you exceptional quality.
Because they generate one token after the next, right? So every word is perfectly conditioned on the entire history of what came before.
Precisely. But that sequential nature, well, it guarantees slowness. And on the other side, you have things like diffusion models that promise this radical speed through parallelism.
But that speed has always come with a quality cost, a degradation in sequence coherence.
Always. Until now, maybe?
And that's our mission for today. We're going to unpack a major advancement that is designed to just eliminate this fundamental conflict. We are diving deep into TiDAR.
An advanced hybrid architecture from NVIDIA and a team of researchers.
TiDAR. It stands for Think in Diffusion, Talk in Autoregression, which, that name just perfectly captures its dual identity.
It's a really beautifully engineered solution, and it targets very specific system inefficiencies. And the reason this is so important is the performance jump you get.
Get this. TiDAR achieves a measured relative throughput speedup of between 4.71 and 5.91 times.
That's tokens per second. A huge jump. And it does this while, and this is the key part, provably maintaining that AR level quality.
Almost 6 times faster.
Right.
We absolutely have to understand how they did this. So let's start at the very root of the problem. Why are those high-quality AR models so glacially slow, especially for, a single user request batch size 1?
It really comes down to physics and hardware bottlenecks. Specifically, it's all about the GPU memory. Standard AR decoding is overwhelmingly what we call memory bound.
Memory bound. So you'd think it's the complex math, the computation that takes all the time, but it's not.
It's not. The latency, the time you wait, is dominated by just loading the model weights and loading something called the KV cache.
Okay, hold on. The KV cache, that's the key value cache. It's basically the model's short-term memory of the conversation so far, right?
Well,
Why is loading that so expensive?
exactly. And the model weights and that KV cache are just massive data structures. They live in high latency memory, usually off-chip DRAM. So every single time, an AR model needs to generate just one token.
Just one?
It has to sequentially load these huge structures. And that memory transfer is the speed limit, not the actual math.
That sounds like an incredibly inefficient use of a powerful processor.
It is.
It's like you're firing up a massive semi-truck, loading it with all this expensive hardware, the weights and the KV cache, just to drive a single block and deliver one tiny letter, one token.
That's a perfect analogy. And because the latency is basically fixed by that memory load time, the GPU's just sitting there idle for most of that cycle.
Okay, so here's the opportunity.
This is the core insight that TiDAR exploits. The researchers call them free token slots. They profiled the hardware and found that the wall clock latency for a forward pass stays pretty much flat,
Almost identical.
even as you increase the number of tokens you process within that single pass.
So if the latency is fixed by that memory load, you can process several tokens for the price of one in terms of time, at least right up until the point where the actual computation finally becomes the new bottleneck.
Precisely. If you can decode multiple tokens in that one forward pass, that one trip for the semi-truck, all those tokens share the huge overhead costs of loading the weights and the KV cache.
Yeah.
This just dramatically increases your compute density.
More throughput, no extra latency. This is the hardware efficiency that TiDAR is built on.
Exactly.
But this brings us right back to that fundamental mathematical tension. Because if we try to process multiple tokens in parallel, we change the whole mathematical structure of the model's probability distribution. And that's where the quality risk pops up.
And this is the crux of the whole design challenge. The gold standard for quality, that's the autoregressive probability distribution. Let's call it the quality mode,
Okay.
a PRA. This is a chain factorized joint distribution, which sounds complicated, but all it means is that the probability of the entire sequence is a product of all the conditional probabilities.
So one token depends strictly and entirely on everything that came before it, the chain.
Yes. That structure guarantees linguistic coherence. It guarantees causality. Now, the speed comes from parallel approaches. like diffusion language models. We'll call this the drafting mode, PIDIF.
Right.
These models try to predict a whole bunch of tokens all at once, conditioned only on the current history. And to do that, they have to assume a degree of independence between the tokens they're generating in parallel.
And that assumption is what breaks the chain.
It's fast,
Yeah.
but it compromises those crucial sequential dependencies. That's the quality tax we mentioned earlier.
So TiDAR's genius isn't just exploiting the hardware, it's creating an architecture that can compute both the fast drafting mode, PDD, and the high-quality sequential quality mode, PIDAR.
In the same single memory-bound forward pass.
Which brings us to the architecture. How on earth did they pull off this mathematical and technical feat?
The secret is a really meticulously engineered component. It's a structured, causal bidirectional hybrid attention mask.
Okay, that is a mouthful. A hybrid attention mask.
It's the blueprint. It literally dictates how the model sees and processes tokens in that single forward pass, which allows it to simultaneously think in diffusion and talk in autoregression.
So let's look at that input sequence. It's not just the old tokens and the one new token anymore. It's what? A combined supersequence.
Exactly. At any given step, you can think of the input sequence as being split into three sections. You have the fixed history, then a handful of draft tokens proposed in the last step that need to be verified.
Right.
And then the bulk of those free token slots, which are basically masked tokens for drafting the next step.
So the model is juggling three different time states and purposes all at once. How does that mask keep them all straight?
It applies two different rules in that single pass.
Yeah.
For the history and the tokens from the last step, the ones that need that high-quality verification, the model uses causal attention.
Standard AR behavior.
Standard AR behavior. And this is critical because this structure lets the model compute that chain factorized PR, our quality mode, which it needs for verification.
That's the verification brain.
That's the high-quality check. At the same time, for the mask tokens in that diffusion section, our free token slots, the model applies bidirectional attention.
Okay.
This lets those tokens attend to each other, which leverages the independence and the parallelism of the drafting mode, diff. This is the engine that quickly thinks up a bunch of possible future tokens.
That is a very sophisticated architectural change. It feels like you're training one model to have two completely different brains. Wouldn't that make training just incredibly difficult, balancing two different loss functions?
It does sound chaotic, but the sources actually explain that this dual mode setup simplifies training because that single input sequence has both the AR part and the diffusion part.
It can learn from both at the same time.
Exactly. The model can calculate the standard autoregressive loss next token prediction and the diffusion loss simultaneously on the exact same data sample.
No need for two separate passes or different data sets.
All right. And they simplified the diffusion strategy with what they call a full mask approach. They just turn all the diffusion tokens into mask tokens. This gives a really dense, consistent loss signal, which helps with convergence and makes balancing the two losses during optimization a lot simpler. The whole backbone is trained holistically.
Okay, so we've got the architecture. It's built for parallelism and for quality. Now, let's jump to inference. How does this translate into those huge speedups, the self-speculative generation process?
The term self-speculative is so key.
Yeah.
Because TiDAR replaces traditional speculative decoding, which is usually a two-step, two-model process.
Right. You have a small, fast drafter model that proposes tokens, and then the big, slow model has to run a second time just to check the work. Two sequential forward passes.
And that drafter is often less accurate, so you can waste a lot of time. TiDAR just eliminates this sequential overhead entirely. In one single network function evaluation, one NFE, the model does both, the high-speed thinking and the high-quality talking.
That is maximum utilization. Let's break down the timing. What is it doing simultaneously in that one pass?
Okay, so think of it this way. While we were checking the homework from last night, the draft tokens from the previous step, we're already drafting the next chapter for tomorrow.
The thinking.
Yes. The thinking happens in parallel, using the drafting mode, TDiffer, and that bidirectional attention. The model pre-drafts the next K tokens. And interestingly, the sources say it conditions these drafts on all possible outcomes of the rejection sampling that's about to happen.
Wow, so it's anticipating the verification.
It is. It's a very clever way to use the full parallelism of the diffusion approach.
And at that very same moment, the talking is finalizing the output.
Correct. The draft tokens from the last step are verified using rejection sampling, which is guided by the high-quality PR that's being computed in the current step using that causal attention mask.
And that rejection sampling is the non-negotiable quality gate.
Absolutely. Only the verified tokens are officially accepted into the final output.
This single-pass drafting and verification, that's where the hardware efficiency really shines. Traditional speculative decoding could never do this because the verifier couldn't also be the drafter at the same time.
And TiDAR uses the base model itself for both roles. It's an incredibly potent combination. The parallel drafting in a single NFE, it just maximizes the use of those free token slots we talked about.
So this is why it's the first architecture that's actually been shown to surpass the efficiency gains of state-of-the-art speculative decoding methods.
Yes, because it can combine those operations into that memory-bound region so efficiently.
What happens to the KV cache then? If, say, the model only accepts 3 out of 5 draft tokens, is that other computation wasted?
That's a key refinement. They manage the KV cache very efficiently. It only needs to evict the cache entries for the tokens that were rejected. So if the final accepted length is shorter than the draft length, the KV cache for the rejected part is just thrown out. No wasted computation, which is a big deal compared to a lot of other complex models.
That brings us perfectly to the results. Let's quantify this. What do the benchmarks say about the real-world impact?
Well, the numbers are compelling, especially on throughput. For a 1.5 billion parameter model, TiDAR gets a 4.71 times relative speedup. That's an average of about 7.5 tokens per NFE.
And for the bigger 8 billion parameter model?
It's even better. The speedup jumps to 5.91 times, yielding over 8 tokens per NFE.
A 6-fold speedup in tokens per second is just transformative for real-time apps. You know, chatbots, coding assistants, anywhere, latency is a killer for user experience. But what about the quality? How do they prove it holds up?
This is where that quality mode, the PR, is so crucial. At the 1.5B scale, they achieved what they call lossless quality compared to the pure AR model.
Lossless.
Lossless. And even at the 8B scale, the loss is minimal, really negligible across all the key benchmarks. And these weren't easy tasks. They used human eval for code generation and GSM-8K for math reasoning. The hybrid approach doesn't fall apart on complex logic.
Now, a big problem with older parallel models was just benchmarking them. Since they weren't strictly autoregressive, calculating the standard likelihood, the true measure of prediction quality, was super tricky. Does TiDAR solve that?
It does, and this is a massive advantage. Because TiDAR's architecture natively supports the PR mode with its causal attention mask, it can calculate the standard autoregressive likelihood instantly, just like a pure AR model.
So it's directly and cleanly comparable on benchmarks like MMLU or common sense reasoning. No more complex debated approximation methods needed.
Exactly. It's both fast and natively benchmarkable against the slowest, highest quality models out there.
You mentioned it surpasses even speculative decoding. Why is the raw acceptance rate better with this hybrid diffusion approach?
It's about capacity and parallelism. TiDAR uses the full capacity of the huge base model as its own drafter, which is just inherently better than a smaller, weaker external drafter. And the parallel nature of the drafting mode provides a higher volume of high-quality potential tokens in that one forward pass. The raw acceptance rate, the tokens per NFE, is just higher than sequential methods can manage.
They also noted something interesting about an internal trust factor, a parameter that controls how much they trust the drafting mode versus the quality mode. And even when they tweaked it, quality was preserved. Why is it so robust?
Because the final check is always that autoregressive rejection sampling. That is the ultimate, non-negotiable quality guarantee derived from PRRs. The system is trained so well that the drafting mode is highly effective. But if it ever slips up, the rejection sampling catches it.
So the speed comes from the parallel draft, but the quality guarantee comes from the sequential check.
Exactly. It confirms the diffusion part is a highly efficient drafting engine, and the AR mode is the quality control that ensures coherence is always maintained.
This has been an incredible deep dive. To sum up the novelty, they found a system bottleneck, that memory-bound nature and those free token slots, and designed a hybrid architecture to exploit it.
And that architecture uniquely computes two competing mathematical paradigms, PIR for quality and PF for speed, at the same time in one pass, maximizing hardware use.
It's a huge step forward, a real harmony between systems engineering and modeling theory. They got maximum compute density without that quality compromise.
For sure. Now, we should mention the limitations the sources noted.
Right, there were a couple.
Yes. The implementation currently needs to double the sequence length during training to fit those extra mass tokens. That could be a slight challenge for extending the maximum context length in the future.
And it was mostly focused on batch size 1.
Right. While it's brilliant for that, They note that maximizing its efficiency at very large batch sizes will probably require some more specialized system optimizations.
That actually brings us full circle, back to the very beginning, and it gives us a final provocative thought for you to consider. The success of TiDAR came from leveraging a very specific memory-bound characteristic of GPU hardware, those free token slots.
Right. It shows that LLM acceleration isn't just about faster math or abstract algorithms. It's about deeply understanding and leveraging system-level hardware characteristics.
So the question becomes, what other system optimizations could be designed specifically for these new hybrid architectures? Maybe custom attention kernels or specialized request schedulers?
Things that could push LLM inference even closer to true, instantaneous, real-time responsiveness for every possible application. Where else can we find these little hardware inefficiencies and turn them into an advantage?
It sounds like the system optimization researchers have a new, incredibly efficient target to aim for. That's all the time we have for this deep dive into TiDAR. We hope you feel thoroughly informed.